Hello and welcome to our session today. This is Bob Lessig at Johns Hopkins. And in this exercise, we will be doing a tour of the PDB database. PDB is the Protein Data Bank. And let's just start the tour by going to the Protein Data Bank. It's a very simple URL. The PDB URL is pdb.org. And what you might immediately notice is that as of November 2013, there are 95,644 structures. That's less than 100,000 known protein structures. Compare that to the number of known sequences, which are in the millions. You realize that there are many more sequences known than there are structures known. Because it is so difficult to develop the three-dimensional structures of proteins, we have many, many fewer structures to work with than we do sequences. I'm going to take you right to the Molecule of the Month, which is a popular tool in the Protein Data Bank. In this case, it's called SNARE proteins, which are small membrane-enclosed vesicles. Now, at the time you view the PDB, it's probably going to be a different protein, but there's usually a lot of nice information about very particular types of proteins, including some three-dimensional structure information, and some high-quality images, and also some interactive structures. If I click that, you will get a Java window that will allow me to view this structure from different angles. And here is the JMOL version, and I can view from different angles by clicking my mouse and turning it different ways. So backing up to the main PDB page, I can actually just click the PDB logo, and that will take me back to the front page. You can search by different terms, by the author, for instance, who's develop the structure of that particular protein. Typically, it's done by the type of protein. So I'm going to go back and put in ribonuclease. I know there are a lot of ribonuclease structures because ribonuclease is a small protein. It was one of the first proteins to have a structure developed. Once you begin to type in ribonuclease, you see a real plethora of shortcuts, including ribonuclease A, H, some different enzyme commission numbers. I'm going to click ribonuclease A. It's going to give me a series of results, and the results are summarized in a very nice table. I can see that there are 224 from Bos taurus, which is cow. There are 13 known structures from human. Say I want to look at the human ribonucleases, so I can click the human, and it says there are 13 of them. So when I click that, my results will now only show those 13 human pancreatic ribonucleases, in this case, for the first ones. Some mutant versions. So you can look at the structure of the normal or wild-type ribonuclease. You can also look at the three-dimensional structure of a particular mutant. In this case, amino acid 28, 31, and 32 are changed in this particular mutant ribonuclease. Let's look at the X-ray crystal structure of a dimer of human pancreatic ribonuclease. You can see that it was released on October 2nd, 2013. I'm going to click that and note that the identifier is 4KXH. All PDB identifiers are 4 characters. They can be letters or numbers. Now be very careful because PDB interchangeably uses zeros and O's, also I's and 1's. So, in other words, 3L07 is not the same as 3L07. They could be different structures. It can be a little bit confusing, so be very careful and be aware if you're searching by identifier, whether that's a 1 or an I or a lowercase l or a 0 or an O. First of all, some information. This is a crystal structure. There are 2 types of structures in the Protein Data Bank, crystal structures and solution structures. The difference is that crystal structures were developed by X-ray crystallography, which is a long process that involves making crystals of the protein and using X-rays to determine the structure. It's a very intricate process that usually results in a high-resolution structure. The solution structure is done by nuclear magnetic resonance, or NMR, and NMR is not quite as powerful in resolution. It really only works on smaller proteins. So in this case, this crystal structure should be fairly good in resolution. If I scroll down a little bit on the right menu, I'll see the experimental details box and note that the resolution is 2.70 angstroms. And crystal structures can range in the 2 to 3 angstrom range. The lower the angstroms, the higher the resolution. And going back up, you can see that this structure was submitted in 2013 in ACTA Crystallography. And the authors' names are listed here. Actually, all of the authors, if you run your mouse over them and you click that author's name, you will get all structures that were authored by that particular author. So these are all usually searchable terms. Almost anything in blue in the PDB page is searchable. Now you see the molecular description. This is ribonuclease pancreatic. Its enzyme commission number is 3.1.27.5. That's a unique identifier based on enzyme type. Organism is Homo sapiens. This is a human protein. And you see some graphics that explain a few things about secondary structure. For instance, this red box under secondary structure represents an alpha helix, and the tan box, or beige box, whatever you want to call it, represents a beta strand. So this is the protein from the N-terminus. The N-terminus is always shown on the left. That's the amino terminus of the protein. The C-terminus is always shown on the right. That's the carboxyl terminus of the protein. It looks like the N-terminus is primarily alpha helical. The C-terminus is primarily beta strand. Here is a view of the structure. And there are different viewers that you can download to view this in different arrangements. For instance, if I click on it, I get a larger view of that. And I can get interactive views by choosing some of these downloadable viewers. You see the summary. It was deposited to the Protein Data Bank on May 26, 2013. And released on October 2nd, 2013. You see that there's one chain in the protein for one polymer. It is from Homo sapiens. You also notice that E. coli is shown here. And typically, when protein structures are developed, the gene for the particular protein was taken out of humans and cloned into E. coli so that you could get enough protein out of E. coli to develop crystals and develop a crystal structure. So this is a human protein that was cloned into E. coli. The protein was isolated from E. coli, and then X-ray crystallography was used to determine the structure. It looks like that there are chloride ions, sodium ions, and sulfate ions that associate with this particular protein structure. And then there's some external annotations like the PFAM classification. It says there's one domain. One known protein domain. If I click that, that would take me to some information about that particular domain. This is a pancreatic ribonuclease. So PFAM is a database of hidden Markov models that describe specific elements that are found within proteins. In this case, it had the ribonuclease motif. You'll also see a series of tabs. Summary, three-dimensional view. I can click three-dimensional view. And now I'm back to the JMOL version where I can get an interactive version of this particular structure. Okay, so here is the particular protein. Now note that the 10 arrows represent beta strands, and this is the dimers. This is 2 copies of this particular protein. And you can sort of see that there's 2 separate molecules. Red ribbons represent the alpha helical sections of the protein. You can use your mouse to drag, rotate, zoom in, zoom out, and get particular information on where you are in the particular structure. You can also export that particular image in different file formats. Basically, it's taking a screenshot of the image and the view that you had. If I want to look at the actual sequence of the protein itself, I can click the Sequence tab. And here is the sequence with the structure. So you see those sort of pink helices represent alpha helical regions, and the yellow arrows represent the beta strand regions, and the amino acids are listed below. If I want the protein in a particular format, FASTA format's the most common, I can click FASTA, and that opens a text file that you see here. I'm going to go ahead to the Geometry tab. The Geometry tab gives you some really detailed information about the three-dimensional positions of very, very specific atoms within the protein. In particular, there's something called the Ramachandran plot that I want to click on, which will open a PDF file. PDF file gives you the Ramachandran analysis, which basically tells you where the bond angles are in this particular protein and shows you if there are any outliers. In this case, there are no outliers, meaning that this structure fits the normal range of bond angles that are associated with most proteins in nature. Ramachandran analysis is roughly diagnostic. This particular plot will generally tell you whether or not your protein model is feasible. I can click the Sequence Similarity tab. What Sequence Similarity will do is identify other proteins in the database that are very, very similar in sequence. For instance, only one particular protein is 100% identical to the protein that we're looking at. However, there are, if I click the 10, it will show me 10 different structures that are at least 95% identical in sequence. So it'll basically show me other structures that may be very, very similar to the structure I'm looking at. So you see there are a series of PDB numbers that fit that particular cutoff of 95% identical to 4KXH in sequence. If I click 3D similarity, what that will do is show me structures that are similar not in terms of sequence, but in the three-dimensional structure level. In this case, it found no other structure alignment results that really match the structure of this particular protein. And the Literature tab will show me journal articles that are associated with this particular protein. Because this protein was submitted in 2013, there is just the one journal article regarding this particular structure. This concludes our tour of the PDB database. Feel free to search this database and poke around a little bit and look for structures that you may find interesting. For more information, please contact us at the Center for Biotechnology Information.